So we are here again. Make sure audio is nice and loud. Okay, we left off on the Garnet system. So this will complete our discussion on lithium-ion solid electrolytes in the context of increasing ionic conductivity, although we will come back and talk more deeply when it comes to interfacial engineering, because that's where all the chemistry and material science lies, really. Why? Right, so to recap, we left off discussing the Garnet systems and how they've evolved in terms of synthetic design to really maximize their chemical stability against lithium metal, intrinsic ionic conductivity, particularly at room temperature, but also at high temperatures. But we'll see that the theme amongst lithium-ion solid electrolytes, of course, is that these materials are highly sensitive to synthetic conditions. They're highly sensitive. The properties are highly sensitive to synthetic conditions. They're highly sensitive to processing conditions after synthesis, and of course, then fabrication into a cell as well, because that's where the chemical decompositions against lithium and also high voltage cathode materials will occur. Now, when I say sensitive, I mean that's something that we have to look out for, not necessarily a negative thing that these materials are sensitive if the decomposition products are actually useful, as in they stabilize, a solid electrolyte interface so that further decomposition is impeded. So quite challenging to track and understand in situ, but there's been a lot of leaps that have been made to actually pinpoint, destabilization mechanisms. So that will be discussed in the electrolyte module, as well as the materials characterization module. Okay, so we left off talking about mechanical properties of these garnets, why initially they were looked at as really promising materials for not only high ionic conductivity, but also chemical stability against lithium and blocking lithium filament growth, right? You probably have heard of lithium dendrite growth, but of course, dendritic formation is a thermodynamic solidification procedure. So if you're not operating in the liquid phase and you're not solidifying, you're really growing filaments. So that's why I use the term lithium filament as opposed to just lithium dendrite specifically. So the theory has been that if your elastic modulus is high enough, then this material can block and impede lithium filament growth. Well, that as a first pass is true, but the situation is more complex, as in you could have softer polymeric materials that will also impede lithium filament growth based on the chemistry of the polymer. So it's not always true, but it is a good guiding principle to start off with. So this is advantageous for this particular material. So that's what we see here. We see extremely high elastic modulus here, for a variety of compositions with aluminum substitution in lithium lanthanum zirconate type compounds, or LLZO. Yes.
Yeah, so I noticed this group on the screen here, but I was wondering, what are some efforts people have made in order to model dendrite growth? Is there a way to ever model it, or is that something that's beyond our capability?
No, it is not beyond our capabilities. Okay, I'm not including myself in our being the general materials community. So some of these authors are modelers. They are computational material scientists, computational chemists, along with one of the first people to really look at Thanga Durai to look at LLCO and actually lithium lanthanum, niobate, and tantalates. And so it is not beyond capabilities, but what are the current capabilities, right? So if you want to model lithium filament growth, that is a dynamic process. And typically that has to be modeled with perturbations to the ground state, right? So the molecular dynamics type of simulations need to include parameters that are not static, like density functional theory, right? If you deposit one lithium atom on, let's say, as an add atom, as a nucleation point to a surface, that is a good starting point as a very static model. But of course, I think we're quite familiar, but if we're not, density functional theory is 0 Kelvin and 0 pressure. So, so perturbations like U parameters, like the Hubbard parameter, and other additional terms that are sort of semi-empirical have to be inputted. So it's not at the limitation of, I wouldn't say ab initio, there are ab initio limitations, but ab initio has to be appended with some semi-empirical feed input of information. So then, if you input something that's semi-empirical, is your method no longer ab initio? I mean, that's for the, that's for the modelers to decide, since that's their expertise. But, as an experimentalist, that's how I view modeling these types of conditions. I think maybe your question also targets a more continuum type model where you lose information at the granular atomic level and you go to more of sort of like properties that you could feed in, like elastic modulus of, let's say, a nanocluster or more thin film type material or what have you. And I think moving to more of a continuum model, I think then you could get a better understanding of the growth itself, as opposed to just like an atom here and there in a more like DFT or even molecular dynamics type model. There you're dealing with molecules, yes, but it's still at that in-between level where I think you might need one step up and go to a continuum type model. But it can be done. Certainly these groups are good at doing all of the above, and of course all their papers go into way more detail than I can actually comment on as a non-expert in modeling. But you already see here that while these elastic moduli are calculated, they are specified as DFT at 0 Kelvin or extrapolated to, let's say, room temperature, right? So something that has a little bit more energy, you feed in some KBT, and now it's a value that resembles something at room temperature when the calculation is really done at 0 Kelvin. So useful, it still builds our understanding, but there are some limitations. And of course, we take that with not a grain of salt, but we take that all into consideration. And so when I take a look at this, I think, okay, well, there's a range. Obviously, the order of magnitude is similar. We're talking about 100 gigapascal or so. That's still more significant than, something that is very soft, like lithium of 5 or 10 even gigapascal, right? So it's good enough for understanding some fundamental processes. In terms of experimentation, there's a lot of work that's been done already on, not even looking at the atomic scale of how these filament growth, but really just wetting properties of lithium onto these oxide-based materials and how better to wet the material, better wet lithium onto these oxide surfaces and how to better coat them. So I only have one slide on that, but the body of literature is quite vast on that within the last, I would say, 5 years on understanding wetting properties, because uneven wetting properties is, of course, then really promotes uneven growth of lithium. So what you want is uniformity at the interface. Oh. Okay. Oh, okay. So my reasoning for why I use the term lithium filament growth as opposed to lithium dendrite growth is a purely thermodynamic reason. Dendrite growth, by definition, occurs when you have a solidification process. So if you're going from a molten state or a liquid state to a solid state, that's when your dendrites can grow. So that would be applicable if you were, let's say, using liquid electrolytes, say, and you're depositing from the liquid lithium ions in the liquid state into a solid form, and that's where the dendrites grow. That's fine. But here, if we're talking about a solid oxide versus lithium, you're having a solid. There is no solidification, right? You have lithium metal deposits, but that's not a solidification process. Literally, L goes to S. It's a solidification is just fundamental material science concept. So by the technical definition, if you have solid on solid, nothing is solidified, but you have lithium filaments growing. And to be more precise about that, the distinction also is that you don't always have dendrites. Like by the definition of what a dendrite is, you know, you have fractal symmetry. There is lithium filaments that grow don't necessarily have that symmetry either. And thus it's really, when you look at it, you know, when you do the characterization, these filaments kind of look mossy. So sometimes you'll see that in the literature, that terminology in the literature as well, mossy growth, filament growth, dendritic growth, all of those terms, I think more or less convey the same message, which is redeposited lithium metal is not growing, is not being deposited uniformly. And of course, your filament is growing and then eventually shorting. It all conveys the same message, but the technical term I try to distinguish so that dendritic growth means something else in the material science definition. Okay. So continuing on with garnet materials design. So in terms of the evolution of this material, right, you've seen perhaps LLTO, so it's lithium lanthanum titanate base compounds with some concentration of vacancies here that are charge balanced with the lanthanum composition. And so LLTO has evolved to this lithium 5, lanthanum 3, M2O12 garnet type structure. And originally, niobium and tantalum were introduced to basically replace the lithium reducible titanium. Okay, so titanium was being reduced, and of course, if your titanium is being reduced, then your original oxide compound is going to fracture, and then it's going to decompose, and it doesn't preserve its original property. So that was the original thought back in the late 80s, through the 90s, early 2000, and they're all cubic structure. And in fact, lithium 5, lanthanum 3, M2O12 was originally looked at as a ferroelectric material, as a lot of oxides were back in this time, you know, the late 80s, early 90s. So the original, you know, X-ray diffraction that looks at this type of material, you can see the outline of this cubic structure where you see chains of lanthanum, niobate and tantalate with the lithium, you know, in between this sublattice. Now, then you start substituting in, so then you have the tantalum and the niobium. Then you start stuffing the parent phase of lithium-3, actually, lithium-3, lanthanum-3, M2O12. And what people saw was that you can increase the ionic conductivity by stuffing or increasing. So I'm using just historical terms, that's not very scientific, but the historical term is stuffing lithium content 3 to 5 to 6 to 7. And it increases the ionic conductivity exponentially because it's increasing the percolative network of where the lithium ions are, but also it's increasing the disorder in the system, the crystal structure disorder in the structure from lithium-3 all the way up to lithium-7. And so you can go from lithium-3 all the way to lithium-7 by this this tree diagram that you see here. So the increase in lithium concentration going from lithium-5 to lithium-7 will actually bring down the activation energy to like 0.3 EV for lithium ion migration, which is really relatively low, actually. And so, in replacing and substituting in some the tantalum with zirconium, you can also see improvements in the ionic conductivity. Now, when you move to the synthesis of LLZO, however, this is, of course, the crystal structure that people often strive for is the cubic phase as opposed to the tetragonal phase. The cubic phase is the higher ionic conductivity phase. The low temperature tetragonal phase, it has the lower ionic conductivity. And that has everything to do with where the lithium ions sit. Okay. So here, both compositionally and crystal structure wise, when you have lower content of lithium, these lithium ions, so let's say lithium-3, these lithium ions sit on tetrahedral sites. As you increase your concentration of lithium, you're pushing now the lithium ions to also occupy octahedral sites and even off-centered octahedral sites and tetrahedral sites. So what do I mean by that? So here, as you increase the lithium concentration, you have occupation of these tetrahedral sites, but then more increasingly going from 5 to 6 to 7, the lithium ions that sit at this octahedral site, what's normally this 48G, so the multiplicity is 48, these lithium ions also get pushed out to this off-centered, what's called 96H Wyckoff positions. And the fact that they're off-site like that, now they're motivated to also start migrating, and the activation energy comes down because of the Coulombic interaction, the lithium-lithium repulsion. The lithium ions are too close together, they're motivated to actually move and migrate. Okay, so that drives up the ion conductivity of the system, because when you bring down the activation energy, right, you increase the jump frequency as well. Okay, so the relationship that's shown here in terms of the lithium site occupancy, as well as the lithium ionic conductivity, here shown in blue, ion conductivity increases quite a bit as you increase the lithium content per formula unit. So going from 3 all the way up to 7, although there are no error bars here. So I would take, the general trend is that lithium ion conductivity increases with lithium concentration in these garnet type structures. So one of the reasons why you see people synthesize the 7, Li7, Li3 zirconate is for that reason, as opposed to a lower concentration of lithium in these types of garnet systems. Okay, well, how does lithium migrate through the system? Well, here you could see the development of these garnet type compositions over the course of 16, 17 years. And what you see is, as you increase the lithium ion concentration, you also change the way lithium ions migrate through the system. So in this Li5 garnet type structure, the lithium 2 site, what's called lithium 2, migrates via this pathway going from this octahedron to this other octahedron. But this other, as you increase the lithium ion concentration, you modulate it so that the, so it's not just a one-step type path, but it's actually, you know, this sort of saddle, has this saddle signature pathway where the activation energy is brought down, going from octahedral base sharing with a tetrahedral site, and then going on to the octahedral site. So it's not as big of a jump. It's a little bit, it's multiple steps, but each step is lower in activation energy. Okay. So in terms of materials design, the zirconates, stuffing the unit cell will bring down the activation energy. So there are also other ways of bringing down the activation energy, and also making sure that the ion conductivity pathway, you know, actually migrate from the solid electrolyte to the lithium metal. And so this is what I was talking about before when it comes to understanding wettability of lithium onto these oxide structures. So here's one particular technique where the garnet system is, or the garnet material is coated with alumina versus without alumina, so without atomic layer deposition. And so what that enables the lithium migration to do is basically fill in these voids. As you know, oxides, you must sinter them at high pressure and high temperature, right, to really improve the ion conductivity of the material. And then when you have these voids that you see here, you could really build a space charge layer and also introduce regions of inhomogeneity and lower ionic conductivity. And so by depositing alumina onto the garnet system, the wettability, you know, lithium wets it much better. Now, the only issue with this type of engineering, of course, is then you have to think about the decomposition products. So alumina is good, but it can also impede ion migration. So we sort of saw that with the cathode type material, where coating with, let's say, nibates or alumina helps with chemical stability, but can also impede ionic conductivity. So this goes back to our discussion of materials design, you know, and also processing science design and fabrication design all play together. You know, it's always a fine balance of increasing one parameter, increasing the performance of one parameter to then offset the performance of another parameter. So, you know, that's just something one has to, you know, keep in mind when, you know, you're making sort of any sort of improvement to these materials. But that's all to say, that is the world of batteries. But we will get back to that when it comes to interfacial design, as opposed to just talking about the intrinsic properties of the properties of the material as it relates to the fundamental, like, crystal structure and thermodynamics. So the garnet system has been, you know, heavily investigated and been around a long time, right? And of course, they're mostly air stable, which is a real advantage for processing and fabrication of electrochemical cells. But the search for higher ionic conductivity compounds has never really ceased, and obviously continues, and it's an active area of research. In terms of looking at other types of families of compounds that have high ionic conductivity, these lithium superionic conductors or LISICON based materials have been also heavily studied. And I keep saying high ionic conductivity as opposed to superionic conductivity, because generally it is accepted that superion conductivity is denoting that a material has an intrinsic ion conductivity of greater than 10 millisiemens per centimeter at room temperature, right? So this is a discussion of just sort of the evolution of designing materials with higher and higher ionic conductivity. And some of the values that you've seen thus far for the garnets are, 10 to the minus 2 Siemens per centimeter. So obviously much less than 10 millisiemens per centimeter, right? So, but that's not to say we should discount these any material that's less than this, 10 millisiemens per centimeter, because even though they're not at parity of, let's say, liquid electrolyte that are carbonate based, there's still a lot of room for us to improve and increase ion conductivity by changing the composition or changing the morphology or how we synthesize the materials. Okay, so that is the distinction for why I keep saying high ion conductivity. Although you've seen a lot of the discussions of these materials within the realm of superionic conductors. In terms of building up to Thio LISCONs, which of course are some of which are compounds with some of the highest ion conductivities at room temperature that are seen for ceramic solid electrolytes. We first start off with LISICON site materials that have these base compositions and structures. So lithium 3-phosphate, it's not only potentially a good ion conductor, a high ion conductor, relatively high, although I would say it's medium at this point. It's also a good coating material, because if a material has, let's say, run-of-the-mill ion conductivity, not too fast, not too slow, not too high, not too low, relative to, let's say, 12 millisiemens per centimeter at room temperature, it can still be, if ions can permeate and migrate through the coating, it can still be a good material to protect your active material, let's say your cathode, but not impede ion migration. So there are some added value for these materials as coating materials for cathodes. In terms of developing LISICON, so this is from Hong back in 1978 or so. These lithium zinc germanate type compounds allow for ion conductivities at actually at 300 C of not that high, so 10 to the -6 millisiemens per centimeter. So the thinking there is, okay, it's not that high, but how do we increase the ion conductivity? And so the general theme for that is to either introduce atomic disorder or to change the anion, let's say a larger anion, to open up the bottleneck, the diffusion pathway. And so that's what people have done for these type of materials. They've introduced atomic disorder at the cation site as well as the anion sites towards these goals. Okay, so when you take a look at Li3PO4 and also this base structure of Li4MO4, the polyanion can really take place in a number of ways. So this X can be phosphorus, which is the phosphate that you've seen, vanadium, even arsenic, the typical elements for M here in the Li4MO parent phase. M can be silicon, germanium, titanium. And so that's what people have done. People have looked at the N members. They've also looked at the solid solutions of these compositions. And then they've also, do things like this sort of cocktail of elements where you have these fractional, stoichiometries, and then you can drive up ion conductivity from 10 to the -6 millisiemens per centimeter to 10 to the -2. Okay. Just by basically introducing site disorder and also eventually going away from oxides, opening the diffusion pathway and the bottleneck with substitution of sulfide of the oxygen. Okay. So in looking more within the LISICON style family of compounds, we also come across the NASICON, or sodium superionic conductor, as its acronym stands for. And so here, the goal is to, same thing, introduce substitutions and introduce a site disorder to increase the ionic conductivity. And so the cation site within this generic formula of, you have your alkali ion site, and then you can have a trivalent transition metal cation, and then a tetravalent transition metal cation, and then some combination, in between the two end members of the pseudo-binary phase diagram. You get the middle, and then the ionic conductivity increases. So this has been seen for lithium phosphate, lithium germanate, lithium silicates, that the ionic conductivity of the solid solution in the middle, with the composition in the middle, mixtures of the two, that you'll get these increases in ionic conductivity. And so for this particular class of family of compounds, you see that LATP and LAGP are pretty common, and that's what have also been looked at in terms of commercializing solid electrolytes for all solid battery designs. In terms of the ionic conductivity, 10 to the -2 millisievert per centimeter is pretty high, but still not achieving parity with that of liquid electrolytes, and thus supplanting liquid electrolytes. It's still not achievable with just these solid electrolytes just yet. Okay. And the other thing is, of course, we've talked about the intrinsic ionic conductivity properties. The two other pieces to balance out, the materials design and whether or not these materials can be realizable commercially is, of course, when you put it against lithium metal, and also in processing the materials, often you really have to process these powders. You can't just press a pellet, or you can't just deposit down these materials. You really have to either densify, sinter, at under conditions that make it difficult to scale up and manufacture. So fundamentally, they are really interesting materials, and there's a lot of promise, but the second step is a difficult step. Okay. So those are LISICON and NASICON. We move to now Thio LISCIONs. And so the last few years have shown a lot of explosive growth when it comes to really exploring the phase space of these compounds. Particularly starting off with Li3PS4. So it's reminiscent of the parent compound that we just talked about, Li3PO4, where the sulfides now replace the oxide. So it's a different anion. The softer, more polarizable sulfide anions, really enable the lithium ions to move through the lattice faster. And so what you see here is just within the same composition, if you have different crystal structures that are temperature dependent. So there's phase transformation with increasing temperature from this gamma phase to this beta phase to potentially whatever this alpha phase is. But already you could see that you can increase the ionic conductivity by more than 2x by just heating up the material a little bit. So then you have to ask yourself, how do I stabilize the high temperature phase at lower temperature? And this is the question that is being asked now. So how do you stabilize a high temperature phase that is thermodynamically higher in energy, but at lower temperatures? What are typical strategies that one would take to do so? Okay, so you react at a high temperature, quench, and basically arrest the product at that particular high temperature phase. Okay. Yes. You could also go to high pressure if the high pressure phase is also the high temperature phase, which is not always so clear, and that's not always the case, but that is potentially another strategy, is to access a phase that is inaccessible under ambient conditions by changing something like pressure. Yes. And why would you nanostructure it, Patricia?
So it's very small. Like the structure is under a lot of stress to get higher energy stabilized that way.
Yes, but I believe you're dancing around the term increasing surface energy.
Okay,
Yes, right. So yes, that is the mechanistic way of doing it, but the fundamental theory is that you're increasing the surface energy, but you're stabilizing that high surface energy. And that's what nanostructuring does, is that it allows you to access phases that you would not normally be able to access in the bulk under thermodynamic, like ambient conditions. Okay, so increase your surface energy and stabilize a higher energy phase that way. So those are three great starting positions or strategies to access these phases that are typically inaccessible. You could really think about so many ways of agitating and perturbing the system to access like even metastable phases. So you mentioned quenching, which is reduction in temperature at a very fast rate, right? And so that's how bulk metallic glasses are made, right? You get all your cocktail, compositions, 10, 15 elements, metals into a molten state, and then you quench at 1,000 Kelvin a second or a few seconds, and that's how you get bulk metallic glass structure, right? So yeah, so quenching is definitely a way to access these high energy phases. High pressure, yes. There are also really cool ways of accessing metastable phases, like instead of rapidly decreasing your temperature, you could rapidly increase your temperature. And so there are a number of ways to do that, right? There's flash sintering type of reaction. So if you start off with powder precursors, you can, flash sinter into one composition for your product, for your final product. You could think about microwave type technologies, which the ceramic community has also talked a lot about and thought a lot about for the last few decades. So you could really utilize different ceramics type synthetic strategies to access all these high temperature, high energy phases. You could also just, in terms of mechanical perturbations, so ball milling is one, but you could even go one step higher than that. There are really not esoteric, but difficult to access synthetic environments, but it's not impossible. You could apply a shock wave and basically mechanically get all of your precursors to react. That's really high energy type of synthesis, but it's an interesting way of synthesizing new phases that normally you wouldn't get. The discussion, of course, of how reliable and how accessible for manufacturing and scale up, that's a whole nother discussion, but fundamentally, there are many ways of accessing really interesting phases that you don't get. And one of the reasons on top of this is really cool, interesting material science and materials chemistry, is that by accessing these phases that you wouldn't normally get in the bulk phase, you can now have access to lithium ion migration pathways that you didn't have before. And the more you understand how these ions migrate, the better you have at building your fundamental tool set and theories for how to increase the fundamental properties, like the intrinsic properties like ionic conductivity. Okay, so there's my little spiel about why synthesis is necessary. Synthetic exploration. In terms of now doing analogous type of syntheses and materials designed for the LISICON, but now Thio LISCION type systems is instead of the oxides, where we still have the metal being silicon, germanium, or tin, you can now have the same type of compounds, but now the anion is sulfide. And while the range is still, quite wide, 10 to the -5 to 10 to the -2 millisiemens per centimeter, what's really interesting about this system is that if you look at the ion conductivity of the end members of the solid solution, so Li4, MS4 with Li3, MS4, you see that the ion conductivities of the end members are lower than that of the solid solution, the compositions that are in the middle due to disorder. Okay, so that's very interesting. In terms of nanostructuring, this is a highly cited paper. Was exciting to see for a number of reasons. One, ion conductivity is increasing, but also two, the low temperature reaction conditions of lithium thiophosphate, particularly this beta phase that doesn't exist outside of the synthesis, or you can't access this this phase via solid state conditions. So if you were just to take, lithium sulfide and P2S5 and combine it in the solid state and, heat it up to some temperature and then, cool it down, the powders that you get that in the bulk phase, you would get the gamma phase, but you can access this high temperature phase by doing a liquid phase synthesis in tetrahydrofuran at much lower temperatures. So basically just stir the precursors in tetrahydrofuran for like a day or two, or, some long period of time. And then you dry off the THF. And then what temperature you anneal the product at to remove the tetrahydrofuran really impacts the ion conductivity that you achieve. So if you heat treat it to 80 degrees Celsius, you can see the ion conductivity is here. But then if you increase it, the thermal annealing conditions to 140 C to remove as much of the tetrahydrofuran molecules that are coordinated to the beta Li3PS4 to like dry off the system, you see the ion conductivity increasing quite a little bit. And then it sort of decreases after that, but there are no error bars here. They all look pretty close to me, so I wouldn't like over interpret this data set, but it's, there is a significant enough increase here that I would say that's pretty real. So that's pretty exciting. When you first synthesize this material, when you stir in Li2S and T2S5 and tetrahydrofuran at like, some gentle warming temperature like 50 C or 80 C, what you get is actually this amorphous one, and then you stop the reaction. Because tetrahydrofuran is so coordinated to the beta Li3PS4, the X-ray diffraction pattern really shows you that it's this amorphous type, structure. So so you see the nanoporosity here when you zoom in on this, on the scanning electron micrograph. Now, as you remove the THF molecules that are coordinated and you're drying off the powders and it's starting to crystallize a little bit, although it's still nanocrystalline, it's not really crystalline in the bulk that we think about, then the ion conductivity, you can see here, increases a little bit. So that's pretty exciting that a liquid phase reaction can access a high temperature phase and also increase ion conductivity, and the reaction is at lower temperature. Now, that's exciting in terms of materials design. The other part of the discussion, of course, is great. Now you can just have a vat of this stuff and you can just stir and then just scale up, right? One has to then, of course, the sustainability of any liquid phase type reaction, because now what do you do with the solvent at the end of the day? Where's the tetrahydrofuran going? Is it recyclable? Can you upcycle it? Not only recycle it. So, you know, can you purify it in a way where it's reusable? I think there are many ways, there are many pathways to, you know, sustainability, but that's a major point of discussion, which is why we have a sustainability module, is because these reaction, you know, these synthetic designs are really exciting. But in terms of realistically scaling up and reducing our, you know, footprint for new technologies, you know, carbon footprint for new technologies, I think there's a huge asterisk that comes after a lot of this synthetic development that, you know, I think we have to be really quite realistic about, you know, so. But that's next week. So for this week, we'll continue on and talk about the special Thio LISCICON. And here we come to Li10 MP2S12, where M can be silicon, germanium, tin. Of course, the compound and composition that has achieved 12 millisiemens per centimeter, that is comparable to that of 1 molar LiPF6 in ethylene carbonate, dimethyl carbonate at room temperature, is of course Li10 germanium, P2S12. So that's very exciting. But why does it have high ion conductivity? Is it the BCC sublattice of lithium? Is it the fact that there's a percolated network for, you know, these lithium ions to migrate at low energy pathways? All the answers yes. So that's really exciting since 2011. So it's been more than a decade now. In terms of reducing the cost of germanium by incorporation of silicon and tin, there is mixed evidence out there as to the effectiveness of these substitutions for increasing ion conductivity. And in fact, you sometimes get decreased ion conductivity as well as decreased chemical stability at the interface with lithium, because you get decomposition products that are, you know, lithium silicates. So ternary and binary compounds that are easy to form, like thermodynamically, energetically favorable, that are easy to form at the interface. And so there's still a challenge to actually incorporate these compounds, these solid electrolytes, as, you know, into an all-solid system. But in terms of driving ion conductivity higher and higher, these are quite high. Of course, more recently, we've seen computations of lithium borate, sulfides, as well as the lithium indium chloride system that also have extremely high liquid-like ion conductivity. So those are also quite competitive and air stable in the case of lithium indium chloride. So there's a lot of compounds now that can compete with liquid electrolytes. All right. So speaking of high ion conductivity and also air stability, we move on to argyrodites. These have been looked at more recently, but they also have quite a rich history. And in fact, it goes back to like the Greek days, hence argyrodites, which means rich in silver. It's based on the silver 8 germanium sulfur 6 compound in terms of its structure. And so hence the term argyrodites. And, you know, the chemistry is complex, but that is actually really exciting, because that enables you to do is now really play with the composition. You can change the lithium ion concentration, which we've seen can increase the ion conductivity by stuffing the system. You can play around with site disorder with cation substitution. So here you have a tetravalent metal, so like tetravalent element like silicon, germanium, tin, or pentavalent species like phosphorus or antimony. And then the anions could really be all of this. Right? Could be an oxide, could be a sulfide, could be a selenide mixed in with halides and even borohydride. I mean, it's very exciting. Now, instead of talking about all the possible compositions, what I'll talk about is one of the compounds that have been studied widely, which is this Li6M Q5X. So the chalcogenide sits here, and it's typically a sulfur, although there's been sulfur selenium mixing for anion disorder type of studies. But what's really interesting about this compound is that if you look at where the lithium sites are, there are many pathways. There are many sites for lithium ions to sit. And so what that also means is there are many pathways for ion migration, but the typical pathway really is this either this doublet jump in between the two cages, or well, between the two tetrahedra, between the two tetrahedra. Now, in terms of the X position, right, it can be a halide. So it could be chloride, could be bromide, could be iodine. With the bromide and the chloride species, you have quite a bit more of site disorder. So where the sulfide ions sit versus where the halide ions sit, they sometimes will just switch during synthesis. And that's just, thermodynamic equilibrium. You put the precursors in, you shake or, you stir or what have you. In terms of site occupancy for where sulfides can go and where the halides can go, there's quite a bit of mixing that occur for the chloride, the bromide. The iodide system is quite large, and so it's anchored to those 4A, 4C sites. It's quite ordered, which is not a good thing because that means your activation energy is much higher than for a disordered system. So the chlorides and the bromide system introduces a lot of site disorder, which will increase ion conductivity. Okay. And so that's what you see here. You see in terms of lithium ion conductivity on this log scale versus the number of site disorder. If it's an ordered system, then there is no site disorder. The halide ions sit in their particular Wyckoff site, the sulfides sit in their Wyckoff site, and so ion conductivity is quite low. But then as you introduce bromides and chlorides, ion conductivity increases. So the site disorder also, what it does is it enlarges the site, this cage of where lithium ions are. And so by increasing this cage, it makes this bond, this lithium sulfur bond, a little bit weaker. So breaking that bond is a little bit easier. So it diffuses a little bit more rapidly. Yeah, so as you see here, this average distance of lithium to the anion, as it increases, the ion conductivity also increases, and concomitantly the disorder amount also increases. And you can quantify the disorder by doing something like characterizing the material with neutron diffraction, X-ray diffraction, a whole multitude of characterization techniques to really pinpoint where the chloride or where the halide ions are and where the sulfide ions are. And then you can quantify, okay, well, if I'm supposed to have a multiplicity of, X, and I have a little bit less than that, you take the two ratio and you have a disorder, a site disorder parameter, well, times 100. Okay, so really just by doing the synthesis and then doing something like X-ray diffraction and then like a refelt, you can quantify how disorder affects ionic conductivity. Okay. And so that's, quite exciting to see. You could also introduce cation substitution, but one must be careful when correlating increases ionic conductivity with increasing, cation substitution amount, because what you see here is the ionic conductivity increases, but not very linearly. Because now what's happening is you have not only increases in the concentration, the amount of cation that you substitute in, but also the charge carrier. for charge balance, right? The charge carrier concentration is increasing. So, depending on what you substitute the metal cation or the metal site with, you get this sort of nonlinear relationship in terms of increase of the conductivity. But even if it's convoluted, you can see, okay, the ion conductivity is also increasing because of disorder by cation substitution. As a very first pass, high order approximation, low order approximation there. Okay. So also very exciting, but convoluted data. Oh, I am out of time. I will pick up here, but I'll just say in closing, so it doesn't seem so abrupt, that in terms of ion migration due to lithium site disorder, what you're really doing is you're just you're forcing lithium ions to move in a concerted manner, because as you increase lithium ion concentration, you're increasing the repulsion, right? Lithium ions are now next to lithium ions. And so due to this Coulombic repulsion, one lithium ion is going to hop and then the other is going to go with it. And so you have this concerted mechanism of ion migration due to the fact that you have increased lithium ion concentration. So kind of reminiscent of stuffing the parent phase, right? So you see certain themes are coming clear when you look at the different strategies for increasing ion conductivity in oxides and sulfides. Okay, we will pick up here. We'll wrap up with anti-perovskite materials as well as STAR sustainability the next time we meet. Oh, yes. Well, the class doesn't, but I have time.
Okay. Well, I was just wondering, like, what this is for the coding.
Oh, okay. Yeah.
I was wondering what the criteria is.
Ooh, okay. If you had to rank, right, the coating typically is a chemically protective barrier. So it has to be ion permeable. It can't impede ion migration. So that's one. In terms of chemical stability, right, it's typically going to be a compound that is non-reactive or at least reactive, the least reactive material. So that tends to be oxide-based materials. Not always true, but niobates, alumina, zirconia, I mean, the list goes on and on, So there's that. And of course, there's been a lot of studies of using LATP, LAGP, Li3PO4 as protectants around cathode particles. Those studies have been done, quite a while now for protecting like NMC particles, that kind of thing. So, so those are the two starting points. If those, you can't fulfill those two criteria, then, they're really non-starters. And then beyond that, the wettability, does it help the wetting of, if it's against lithium metal, which of course all solid cells are, the geometry is, that is the targeted goal, right? Is that you can stabilize your electrolyte against lithium metal and not decompose. So the coating then for that particular application increases lithium wettability, but also fills in all the voids as well. So, I mean, the ALD would do that, any rough surface ALD coat. So
I guess is the reason why lithium isn't like running nicely to the electrolyte, is there like some sort of lattice mismatch between the something allows wettability?
oh, I see. No, in terms of lattice mismatch, no, because the two materials are not, for conventional fabrication techniques, they're not grown on each other. It might be a different story if you're talking about thin film type batteries where maybe your current collector is the substrate, And then you have some geometry that you're designing, like pillars or whatever, and things are, your active material is actually grown on your substrate, then yes, lattice mismatch is something you want to think about if you're thinking about epitaxial growth. But if you're not thinking about epitaxial growth and you're just thinking about deposition of material onto a substrate, lattice, dysregistry is not necessarily a high prioritized parameter. Okay. I haven't listed like all the parameters, but we could be here all day. So, I'll stop with 3. The top 3 anyway.